Welcome to the Business Analytics lesson on statistical process control and quality. In this lesson, we're going to talk a little bit about quality. We're going to define quality, explain why it's important. We're going to talk a little bit about some of the historical figures in production quality and service quality, and then we're going to learn how to do some statistical process control. We're going to learn to make some P charts and R charts and X bar charts and all kinds of charts to actually allow us to track our quality or our errors. So hang on and let's go ahead and get started with quality. Well, let's start with a definition of quality itself. So the Oxford American Dictionary defines it as a degree or level of excellence. The American Society for Quality defines it as the totality of features and characteristics that satisfy needs without deficiencies. So you got the idea here that quality, we'll discuss it a little bit more, quality is the ability of the product of the service to fulfill its needs and live up to its expectations. Quality can be very subjective, especially when it comes to the consumer's perspective, which is really important. The consumer is going to be thinking about, is it fit for use? How well is the product or service does what it's supposed to do? The quality or the designing quality characteristics into the product or the service. For example, a Mercedes and a Ford might be equally fit, but a consumer is going to certainly probably in most cases define the Mercedes as being a higher quality product. Well, the little image that you see here is one of the first iterations of the pocket hose. And if you ever bought one of those when they first came out, or you knew someone that did, you know that the quality was horrible on those. They didn't last very long at all. In fact, they had a very difficult time trying to rebuild it. And if you ever see an advertisement now for a pocket hose, they're going to stress the quality and how long it lasts. They're trying to undo the subjectiveness of their perspective of being bad quality. Well, it's actually pretty easy to define quality of a manufactured product, and there's a set list of things that we look at. And so the first part of the list here is performance, the basic operating characteristics of the product, how well the car handles, its gas mileage, features. And again, thinking about cars again, does it have basic features or have we added things like Apple CarPlay that are almost a necessity these days, or leather interior? And of course, reliability. How well is that car going to, how long is it going to last before we expect it to break? How long is the TV going to last before we have to buy a new one? We would actually call that mean time between failure, and that's a term that you'll learn a little bit more about as you continue on with business analytics or production operations management. All right, let's continue with the list. All right, continuing on with our dimensions of quality for manufactured products. Conformance is a dimension. That's the degree to which the product meets pre-established standards or guidelines. Durability, how long it's going to last. Serviceability, can we get the parts that we need? Is it easy to repair or difficult to repair? All right, we'll continue with the list here. Okay, finalizing the list of dimensions of quality for manufactured products, we end the list with aesthetics, how well the product looks, feels, sounds, or smells, or tastes. Safety, is the consumer going to be safe in the product? That's very important with automobiles. Many products that you're probably aware of have been pulled off the market because they weren't safe. And then perceptions, and that's subjective perceptions based on the brand name, the advertising, and how consumers feel about the product. If we're in the service industry, there's also dimensions of quality for our service product as well. That list would include courtesy, how well are the customers treated? Are the phone conversations nice? Are people left frustrated? Consistent, is it at the same level every time they call? Do you get what you expect? Okay, rounding out our list of dimensions of quality for service products would be accessibility and convenience. Is it easy to obtain the service? Are they able to answer our calls quickly? Do we have to stand in line forever to get the service that we need? Accurate. Are we getting the right answers every time? Responsiveness. How well do they react to our unusual situations? Is a telephone operator able to handle our questions or at least point us in the right direction? So there we have the list of dimensions of quality for services. Well, here we see a little flowchart or hierarchy of the meaning of quality. And notice that we have two clear paths here. We have the producer's perspective and the consumer's perspective. And so the producer is concerned about production. Are they able to create a product that conforms to the specifications? And Are we able to produce that product within the guided costs that we've given it? We're going to be talking about that conformance to specifications as we continue in this lesson. On the consumer side, we're looking at quality, and of course, we're looking at price. And of course, our perspectives as a consumer are affected by marketing. And finally, the overall judgment here is it fit for the consumers to use, and are they satisfied with that product? Well, this is discussing information that you'd certainly encounter in a marketing class, but it's good to discuss it when we're talking about quality as well. It's extremely important to have satisfied customers. Satisfied customers are less likely to switch to a competitor. If they're satisfied with you, they're going to stay with you. And it costs 5 to 6 times more to attract new customers than it does to keep existing ones. Your existing customers are by far your most cost effective customers to keep. 94 to 96% of dissatisfied customers don't complain, they just disappear. And small increases in customer retention mean large increases in profits. And of course, we know that dissatisfied people are going to tell way more people about their experience than satisfied people are. And of course, with the internet and Facebook and Instagram and TikTok and the others in Yelp, it's so much easier to get the opinions broadcast. And of course, bad opinions are something that we don't want. So we need to satisfy our customers, and we can do that through quality. And just some final thoughts on the importance of quality here. Remember, we had that little chart talking about the producer's perspective and the customer's perspective. When it's all said and done, it's the customer's view that must dominate, or the product will not be successful. And if you've done, a marketing class, which many of you probably have, you've probably heard that the catastrophe with the Arch Deluxe and how much McDonald's spent promoting that new product. And once it was introduced, nobody liked it. They thought it was pretty much the same as all the other hamburgers they've had. And there's been many, many other products that maybe were just fine in quality, but that consumer's perspective caused them to fail. Way back in the early 80s, you had the IBM PC Junior. That's probably shows up in your historical marketing text as well. New Coke, and the list goes on and on and on. So again, if the consumer determines that the product isn't worth the cost, or just isn't of the quality that they expect, it's going to fail, regardless of how much money you put into promotion and even how good the product actually is. Well, we've discussed quality a little bit, and we're going to be getting into actually being able to measure quality and doing some statistical process control. It's important to talk about some of the historical figures and what their contribution was in what we're actually talking about today. So, Walter Sheward in the 1920s developed control charts, and we're going to be using control charts today. He also introduced the term quality insurance. We have Edwards Deming, a very important figure in quality management. He developed courses during World War II to teach statistical quality control. And one of the most important things he taught was the fact that we don't have to test every product, we can just do sampling. And after the war, he went over to Japan, and he helped teach the Japanese companies how to improve their quality. We also have Joseph Jorin. He followed Deming to Japan in 1954, and he focused on strategic quality planning and quality improvement. All right, let's finalize our list of important figures within quality management. We have Armand Feigenbaum. In 1951, he introduced the concept of TQM, or Total Quality Management, with continuous quality improvement. Philip Crosby in 79 emphasized and helped producers to understand that the costs of poor quality outweigh the cost of preventing the poor quality. We have Kaoru Ishikawa, and he promoted quality circles. He developed the fish bone diagram that we're going to talk about here in just a second, and he emphasized the importance of internal customers. Walter Deming, who you might remember from our previous slide, went to Japan and helped teach quality control to the Japanese producers. And he's best known for his 14 points. And so let's go over those 14 points. One was to create a constancy of purpose. What is our purpose? What do we need to do? What are we producing? Number two, adopt a philosophy of prevention. Prevent defects before they happen. Cease mass inspection. Like as I mentioned earlier, you don't need to inspect everything. Let's use sampling techniques so that we can do this and save time. Select a few suppliers. Number four, based on quality. Number five, constantly improve the system and its workers. Number 6, improve worker, institute worker training. And number 7, instill leadership among supervisors. Empower the supervisors, give them power to make changes when needed. Continuing with Deming's 14 points, number 8, eliminate fear among employees. They shouldn't fear that if they bring something to the management's attention that they'll get fired. Number 9, eliminate barriers between departments. Stop the siloing. Number 10, eliminate slogans. Number 11, eliminate numeric quotas. Number 12, enhance worker pride. Number 13, institute vigorous training and education programs. Number 14, really important to develop a commitment from top management to implement the above 13 points. They've got to buy in. Walter Deming is also very well known for his Deming wheel. It is the PDCA cycle. So one is plan, study the process, identify the problems, set goals. Number 2 is do, implement the plan. Number 3 is study and check to make sure it's working. And 4 is act, institutionalize improvement, and then continue with the cycle. Notice that the cycle never ends. It's a continuous process. All right, as we continue our discussion with the quality control, let's talk about some of the tools that are used in quality control. We will encounter things like flowcharts, cause and effect diagrams, check sheets, Pareto analysis, histograms, scatter diagrams, and statistical process control charts. Well, we're going to spend most of our time on the statistical process control charts, but let's go ahead and go over a couple of these others so that you're familiar with the terms at least. Here you see an example of a process flow chart. We have each step in the production process and how it relates to the others, and the purpose of this is to help us identify potential problems in the production process. Here you see an example of a cause and effect diagram, also known as a fishbone. And so we have the different elements in our production of either a product or service. In this example, we have measurements, personnel, machines, methods, materials, and environment, and then sub-items within each of those that we want to evaluate. Here's a couple of other simple tools that we might use in tracking quality. We could have a tally sheet or a check sheet that allows us to tally the numbers of errors for each element. Or we also have a frequency chart that will allow us to diagram the number of problems in each of the areas. Another tool we use in quality management is the Pareto analysis, sometimes called the 80-20 principle. And the Pareto analysis, or the 80-20 principle, tells us typically that within the case of quality, that 80% of our quality problems or defects are going to be caused by 20% of the elements. And so here we see a situation here where staff communication has caused 83 defects, which that percentage would be 64. The 80-20 principle works in just about everything, and usually whether it be HR or anything else, 80% of the issues are usually going to be caused by 20% of the elements. Here we see a bar chart or a column chart of the numbers that we saw with the Pareto analysis here. In this case, that we can see clearly the system and the staff communication are going to be causing the largest percentage of the problems that we're having in this particular company. Here you see an example of a statistical process control chart. It has upper control limits and lower control limits. In the data that we've charted, hopefully falls between the lower limit and the upper limit. If it falls outside of either of those, then the process would be out of control or it would be a defective process. We're going to be spending quite a bit of time developing this as we continue on in this lesson. As you study quality control, either at this level or at a deeper level, you will encounter the term Six Sigma. Now, Six Sigma is a complete process of quality control, but let's just kind of talk about what it means from a basis standpoint here. Sigma represents a standard deviation. And you have an example of a normal curve here, and you remember from your statistics class that 3 plus or minus 3 standard deviations encounters or includes 99.73% of all of the occurrences under the curve. Well, if we have plus or minus 6 standard deviations, which is what the quality control of Six Sigma is after, we end up with 99.9966% of all the occurrences. And that equates to only 3.4 defects per million opportunities. In other words, if we've produced 3. A million iPhones, that we would expect only 3.4 of those to be defective coming off the assembly line, and that would then equate to fulfilling Six Sigma. Here you see the Six Sigma process in a chart. And so the steps are define, measure, analyze, improve, and control. And they're not too far off from the Deming wheel that we talked about earlier. It does adopt some terminology from martial arts, mainly karate, in which we have green belts and black belts. But the goal here again, you go through extensive training, but the goal is just 3.4 defects per million opportunities. And you could become Six Sigma certified, and that is a certification that you will see in industry. It's a very important certification. Okay, now we're going to get into some mathematics. Well, we're going to be creating control charts here, but let's go back to the concept of statistical process control. That is based on the concept of sampling. Remember, Deming said you don't need to test every individual product that you produce. Of course, with some products that's impossible, especially if you're producing ammunition. You can't test every bullet that you create. So we're going to be working with sampling, and through that sampling, we're going to be able to estimate the flaws or the quality in our production process in general. Within our statistical process control, we need to talk about sources of variation. No two products are going to be exactly the same. They're going to vary a little bit, but whether or not they vary enough to be considered a defect, well, that's a different story here. But within our variation, there's two kinds of variation. There's random variation and there's non-random. Random really cannot be completely eliminated unless we have to change everything. Get a whole new factory, change the technologies. But if it's a non-random variation or a non-random variation that's causing an error, we want to look at that a little bit further to see if we can find out what that is and make changes. Maybe we just have to adjust a machine. Maybe we have to make sure our employees take a little bit more breaks or better training. So we can have random and non-random sources of variation. Well, here we see another look at the statistical process control chart. As I mentioned before, we have upper control limits and lower control limits, and then we have the means or the ranges, depending on what kind of chart we're creating, that we're plotting. And notice in this case, we do have one of our ranges or means that is outside the upper control limit, so that would tell us that that process is out of control or it's producing too many defects. Now we're going to learn in the next few slides here how to actually compute the values for the upper and lower control limits, and then we'll be able to create a chart as well to track whether we're in control or out of control. One of the first charts we're going to be creating is a mean chart. A mean chart is going to plot the means within the upper and lower control limits that we saw just a second ago. And there's going to be two variables that we need to understand in order to compute that. We're going to need the grand mean, which is going to be the sum of the sample means divided by the number of observations. We also then are going to need to be able to compute the standard error of the sample means. That is simply going to be the standard deviation divided by the square root of the number in the sample. We'll go ahead and do that, and that'll make more sense as we start computing our upper and lower control limits here. Okay, a mean chart can be based on the standard deviation. If we know the population standard deviation, that makes it very easy, or we could compute the standard deviation of the sample if we have enough sample sizes. So we have two different methods. We could have the mean, or we could also have the mean of the ranges. Now let's go over the upper and lower control limits for working with standard deviation. So the upper control limit, UCL, is the grand mean. We talked about the grand mean in the previous slide, plus 3. And 3 represents the sigma, or the standard deviations from the mean that we're after. And the textbook that I'm basing this on uses 3. That could be 2, it could be 4, it could be 5. If you're doing 6 sigma, then that would be 6. Multiplied by the standard deviation of the sample divided by the square root of n. Lower control limit, very similar formula. It is simply the grand mean minus 3 times the standard deviation divided by the square root of n. Now if we're working with Ranges, when we don't have the standard deviation or we don't want to compute the standard deviation, it's similar but a little bit different in that we have a new variable here called a sub 2. So the upper control limit is going to be the grand mean plus a value that we're going to look up in a table, a sub 2 times the average or the mean of the ranges. The lower control limit, same thing, is just subtracting from the grand mean the a sub 2 times the mean of the ranges. Now, you usually will have tables that will find the a sub 2. We actually use it to find a couple of other variables when we're doing a couple of other charts that are coming up here. But on the next slide, I'll actually show you that table, and hopefully your textbook will have that, or you can find it on the internet relatively easily. Okay, we're going to step through creating upper and lower control limits uh, for means, and that means we're going to be using the standard deviation, either the sigma or the standard deviation of the sample if we have it. So in this case, we have some observations of potato chip ounces. So we have taken a sample. We've actually taken 10 observations with 5 samples each. Maybe these are days, day 1, day 2, day 3, all the way through day 10. And so we've measured how many potato chips are in each bag. So on day 1, the first sample had 5.02 ounces. Day 2 was 5.01, then day 3, 4.94, and so on. And so then we take the mean of each of those. So for day 1, the average weight of the potato chips in that bag was 4.98 ounces. And we go on all the way down. We total them up and we compute then the grand mean by taking the total divided by, in this case, 10, the number of observations that we have. And so we end up with a grand mean of 5.01. Once we have that grand mean, then we can go ahead and compute the standard deviation and then compute the upper and lower control limits. And we're going to do that on the next slide. All right, once we have the grand mean computed, we'll then go ahead and compute the standard deviation, and I've used Excel to do that, and I've computed the standard deviation of this sample of being 0.05737. Then I can go ahead and create an upper control limit and a lower control limit using the formula that we just saw. So the upper control limit is going to be the grand mean plus 3 times the standard deviation divided by the square root of n. In this case, n is 10. So then we have the lower control limit, grand mean, minus 3 times the standard deviation divided by the square root of n again. So we have an upper control limit of 5.065 and a lower control limit of 4.96. And so what that's telling us then, as long as our mean is within that range, that it is in control. Well, the next step after we've computed the upper and lower control limits is to actually create a chart so that we can see whether our data is fitting within, if it's in control or out of control. So the easiest way to do this, to create a chart in Excel, if you're using Excel or some other spreadsheet software, is to actually create 2 additional columns and put in the constant value for the upper and lower control limits. And that allows you then to graph the mean, the upper control limit, and the lower control limit in a line chart, and I'll show you the result on the next slide here. Well, after adding the columns for the upper and lower control limits, we can actually then create a line chart using those 3 columns, and you see the result here, a very simple Excel chart. Notice that for day number 9, we are out of control. We have exceeded the upper control limit, and that would tell us in this case that there's something to look at, or maybe it's either random or non-random. We want to look at day 9 to see what that was all about. Did somebody not show up for work? Did a machine break? You get the idea here, but it's very easy to do that once we've created a mean chart. Right, when I showed you the formula to compute the upper and lower control limits for a mean chart based on the mean of ranges, we talked about the control factors table here, and you notice that there are 3 columns here. There's at the far right the D3, D4, which we'll see later. That's for an R chart. Don't get that confused with a mean of the ranges that we're doing now. So for an X chart or a mean chart, we have the A2 factor. And so we're looking at the sample size. In this case, the sample size was 5. And so the A2 factor that we're using here is 0.577. And once we've determined that, we can create an upper and lower control limit for the mean of the ranges. Okay, so using the example in this case, then what I've done now is I've also computed the range, and in Excel I've just used the max minus the min, and so we end up then with the range of each of the different days. And so for day one, the range was 0.08. So once I've got that, I'm then going to go ahead and create an average or a mean of the ranges of 0.115. Then I looked up that a sub 2 factor, and then I can compute an upper and lower control limit. In this case, with the mean of the ranges, my upper control limit is 5.076, and the lower control limit is 4.944. And I don't expect that you remembered what they were when we use the standard deviation, but at least with this example, they're pretty darn close. So here you see the comparison of the two methods here. So again, using the standard deviation, the upper control limit was 5.07 and the lower control limit 4.96, using the mean of the ranges, again with this illustration, but in general they're going to be pretty close, 5.08 and 4.94. Well, the next chart we're going to create is an R chart, and of course R stands for range. Now we used range before, but that was the mean of the ranges. Now we're actually going to chart the actual ranges themselves for each day. Now in order to do that, we're going to need two additional factors for the R chart, the D3 and the D4, and we find that on the control chart factors table, and we'll step you through creating an R chart now. Okay, for a range chart, an R chart, the upper control limit is going to be the D sub 4 from the table times the mean of the ranges. Lower control limit is the D sub 3 times the mean of the ranges. All right, and of course we're going to end up with the mean of the ranges by summing up the ranges and then dividing by the number of observations. In this case, that would be 10. Okay, I've computed the mean of the ranges, which we did earlier, but now using the D sub 3, the D sub 4 from the chart, we end up then with a lower control limit of 0 and an upper control limit of 0.24311. All right, I add those to columns in my Excel data so that I can actually chart them and see how it looks. Well, here's an R chart I created in Excel from the example data, and we can see that all of the ranges are within tolerance in this case. None of them fall outside the upper or lower control limit. All right, there's two other charts that we'll talk about briefly here, the P chart and a C chart. P stands for proportion, and a P chart graphs the proportion of defects in a sample. A C chart counts the number of defects in a sample. That'll make more sense as we continue on here. Mean charts and R charts are the result of measuring something, measuring a range or measuring a mean. Sometimes though, we either just determine it's good or it's bad. And in that case, we would use a P chart, and the P of course stands for proportion. So what we're going to be doing is creating the proportion, computing the proportion of the total number of defective divided by the total number that we sampled. We're then going to create or compute the standard error of the proportion. Once we have the standard error of the proportion, we are then going to be able to create upper and lower control limits using the formula here. And we'll step through an example and see how that works. All right, we're going to go ahead and construct a P-chart now. Remember, P-chart is a proportion, it's defective or it's not. So we're using an example of, we have 20 days that we've looked at 100 pairs of genes. Don't have all the data here, but for instance on day 1 we found 6 pairs that were defective, and so 6 out of 100 gives us a proportion of 0.06, and so on and so forth here. Okay, so from there we're going to be able to create the upper and lower control limits here, which we'll do here in the next slide. Okay, so the first thing we're going to do is compute the proportion. That's the total defectives divided by the total sample observations. So with this example, we'll assume that we found 200 pairs of genes out of those 20 days of 100 pairs each that we looked at that were defective. So we have 200 divided by 20 days at 100 each that we looked at, and we end up then with a proportion of 0.1. Well, once we have that, we're then able to go ahead and compute the upper and lower control limit. So the upper control limit is the proportion times the z, which in this case we'll use 3. So we have 0.1 plus 3 times the square root of, which is the standard error, of the proportion here, we have zero point 0.1 times 1 minus zero point 0.1 divided by 100, and we then end up with an upper and lower control limits computed of 0.19 for the upper and 0.01 for the lower. Next, we would just plot each day's proportion, and so that we can see that over 20 days here, we have at least one that is out of control. We also see a trend. It looks like it's trending to more errors. So there's something there that we might want to look at here. But that's how easy it is to create a p-chart. Remember, a p-chart is a proportion of errors you're counting, bad or not bad. A C-chart is different than a P-chart. Remember, with a P-chart, we're counting a proportion of defects. We're throwing it out if it's bad or not. A C-chart is about the number of defects in a single item. So let's assume maybe that we're looking at, well, the example here is as a hotel room. And, we have a certain tolerance of how many errors. Maybe the bed isn't turned down just properly, or the mint was in the wrong spot, the towels weren't folded properly. So we're going to allow some errors, but we're going to count the number of defects in the sample that we're doing, and then we're going to be able to create an upper and lower control limit from there. So in this case, we have 15 samples, and we've counted the number of defects that we found in each room. So on sample room 1, we found 12 defects, and so on and so forth. So all the way down through the 15 samples, we found a total of 190 defects. So then we have the average number of defects, which in this case is 190 divided by 15, or C bar then would become 12.67. The upper control limit, the formula for that is C bar plus the z-score, which could be 3, most commonly used, sometimes 6 if you're doing Six Sigma, divided by the C bar that we just computed here, the square root of that, of 12.67. And so then we end up with an upper control limit of 23.35 defects allowed, a lower control limit of 1.99. Of course, in most cases you'd want that lower control limit to be 0, but the same formula is involved there. All right, let's go ahead and look at the C chart and see how it looks in a chart format. All right, here's the chart with that example data I was describing here. We have the number of defects, the average number of defects computed for each of the samples that we took. And in this case, we're well within tolerance. We haven't even gotten close to the 23.35 upper control limit. Well, that's going to conclude our quality and statistical process control lesson. We threw an awful lot at you. Hopefully it makes a little bit more sense. And if you did find this video helpful, please consider liking it. Please consider subscribing to my channel. And there are many additional resources out there on my website, luthermaddy.com. Thank you very much, and we'll see you in the next video.